Hello everyone, welcome back to Physical Geology, I almost said Historical Geology, Physical Geology 1403. Today is lecture 6, we're talking about sedimentary rocks. But as per usual, you have an opportunity now to ask me questions. Anything that we've talked about previously, or anything interesting that you've heard about. Any questions? Any thoughts? Comments? Songs, dances, jokes, anything?
What can make a snake bite you?
What can make a snake bite you? That depends a lot on the snake. Firstly, it depends.
This exact snake right there.
If you posed a threat to its life, my snake would bite you. Or if you irritated it by, say, trying to grab its head every now, too much, it might snap at you to say, hey, knock it off, punk, right? Those are really the only circumstances under which my particular snake would bite you. He would never bite you with the intent to eat you. That's impossible. Even he knows that. Okay? So you're fine. You don't need to worry about him biting you at all, unless you're being intentionally weird with him. In which case, I would take him away from you well before then. Okay? What else?
What do you normally feed him?
Oh, what's that milkshake there you're drinking?
I feed him a rat about this big every other week. The milkshake. This has kale, cayenne pepper, almond milk, protein powder, a superfood blend. It's got a whole bunch of stuff in it. Yeah. Normally I will have finished my breakfast before I come in, but my late night last night led to a late morning this morning, so I'm going to be continuing to drink that throughout the lesson today. Hope you don't mind. All right. What else? We good? All right. Should we talk about sedimentary rocks then? We should. Let's do it. Okay, so we've already talked about igneous rocks. We talked about the rock cycle up to the point of we've gone through magma turning into igneous rock. Igneous rock goes through a process of weathering and erosion, which other rocks go through as well, but we use igneous rock as an example. Okay, so now we are at the point where we have this broken down material called sediment, right? Now what happens to that sediment? That's what we're learning today. Now, that sediment goes on to make a type of rock called sedimentary rock. I know, imagine that. Pretty crazy. 90% of our Earth's crust is igneous and metamorphic. Igneous you've learned about, metamorphic you'll get next week. 90% of the crust are those two things, but about 70% of all the rock on the surface, what does that mean? Exposed to either ocean or atmosphere, right? The surface, the outermost part of the crust. About 70% of that is sedimentary rock. Okay? So this makes it very relevant to us because where do we live? On the surface, right? Aside from a few solitary mole people who may or may not live under the surface, right? I know a lot of people who intentionally build their homes deep underground, which is actually really cool, and I would love to do that someday.
You have friends that do that?
Yeah. It's just they're essentially like super deep basements or bunkers. Right? I would love to have a bunker one day. I'd turn it into a man cave / fallout shelter because you never know, right? But we all live at the surface, okay? And most of the rock here is sedimentary because of the processes that occur here. What processes occur here at the surface? Weathering and erosion. And what does that make?
Little smaller rocks and sediment.
The sediment. Bingo. Weathering and erosion, that's going to make and transport our sediment around, which in turn makes that sedimentary rock. Boom, bada boom. Most of the rock on the surface, exposed at the surface, is sedimentary. Okay? So sedimentary rocks are cool, not only because they are very relevant to us, but also because they preserve evidence of past processes. Igneous rock, we learned about how you could interpret igneous rock to figure out some things from Earth's history. Cool. I'll teach you about how to do the same thing with metamorphic rocks next week. But sedimentary rocks, if we can get this much information about Earth's past processes from igneous rocks, we can get this much from sedimentary rocks. That's huge, okay? Because the process of creating, moving, and depositing that sediment saves a lot of stuff in it. What do I mean by that? Well, what if there's running water depositing my sediment? What if that sediment is changed, affected in some way by that running water? Say, ripples, right? What if dunes are formed? What if something dies in that sediment and is preserved in it? What does that make? A fossil. All of these things happen in sedimentary rocks. You can't have fossils in igneous rocks. How come? Yeah, exactly. Igneous rocks are formed from magma. Fossils not going to survive in magma, right? You also can't get fossils in metamorphic rocks. You haven't learned about that yet, but they would not survive the process of metamorphism. Okay? Sedimentary rocks are the only kind of rock that we will find these fossils in. Very valuable for that reason. Also, a lot of our more precious resources are found in sedimentary rocks. Name a precious resource.
Diamond.
Gold, diamond. Well, diamond we can actually find in igneous rocks. Emerald we can also find in igneous rocks. I'm talking about a more generic... Is diamond and emerald really the most common resource y'all can think about? Huh? Aluminum we often find most accessibly in sedimentary rocks, like that bauxite I told you about last week. Silver. Oil. How about that one? Guys, we live in the Permian Basin. Oil wasn't the first resource that I heard. Did you say it? I'm sorry, I didn't hear you, Aaliyah. You can yell louder at me, all right? Just go, oil, next time, and I'll hear you, all right? Okay. But yes, only found, oil, only with a few exceptions, found in sedimentary rock. An exception, in Vietnam, there is a place that you can get oil out of the ground, but it comes out of granite, okay? Which is weird, but it wasn't formed in the granite. It's only in the granite because that's what's holding it. It was formed in a sedimentary rock, like all oil is, and then migrated into this cracked granite formation, and they drill into the granite to pull the oil out. That's the only weird circumstance where you can get oil out of igneous rock, okay? But everywhere else, it comes out of sedimentary rock. Gavin, I'm sorry, would you grab that door for me? I completely forgot to ask at the beginning. The campus police get on my case if I don't close the door, especially if I have high school students in my classroom. That door always has to stay closed for security reasons. Okay. Let's see. Where was I? Right. Sedimentary rock. Resources. We get a whole bunch of stuff out of sedimentary rock, fossils, and resources. So, where are we in the rock cycle? We have gone through everything up through weathering and erosion. What happens after that? Remember, weathering is the breakdown. Mass wasting and erosion are both different aspects of transport. Deposition. That's the next thing that happens. What do you suppose deposition is?
Whenever the sediments, they fall, they stop moving and they start building up.
Yes, it gets deposited. Deposited means exactly that, Jackson. It stops moving. Wherever it is, it stops there. And you start forming, I heard this word over here earlier.
Sediment.
The sediments are forming
Layers.
layers as they pile up on top of each other. Bingo. Okay? Then after that, there's something called diagenesis, which we will talk about later on. But essentially, diagenesis is any change that occurs to that sediment after it's deposited. Off the top of your head, can you think of any change that might include?
Ooh, like a river just stops. It's like there's a wall in front of it now.
Rivers don't typically just stop. Even when you put a wall in front of them, they simply divert another direction. What are we talking about today? What's the subject? Sedimentary rock. So at some point, my sediment has to turn into a sedimentary rock, right? At some point, all this loose sand has to turn into a stone. That process is included in diagenesis. Okay? Any change that occurs to that sediment after it's deposited, including becoming a rock, is in diagenesis. We will talk about that in a bit. But first, I'm going to tell you how we differentiate between sedimentary rocks. We're going to classify them into different categories, and these are the methods that you're also going to use on your lab. Okay, so bear that in mind. Very useful. Take great notes, right? Okay, the first category is clastic. Clastic sedimentary rocks are those which are formed out of the broken bits and pieces of former rocks. Okay? So, remember, mechanical weathering is that physical breakdown. And that gives you the stuff like sand and silt and clay and little chunks of say, gravel and things like that. Anything that physically breaks down a rock is making clastic fragments. And so our clastic sedimentary rocks are going to be made out of those fragments, out of those physically weathered sediments. Okay? Then you've got non-clastic. And these are going to be made out of primarily ingredients from that chemical weathering process. Can anyone remind me what chemical weathering is? Huh? Yeah, what's happening to the bonds? They're breaking apart. Not because we're hitting the bonds with a hammer, not even because I'm heating it up. It's chemically breaking apart. Like, say, through an acid. They're being disassociated. The bonds are simply being disassociated from each other, right? And so you end up with loose potassium ions and calcium ions and bicarbonates and silica ions and all these byproducts that we talked about. And they're just flowing through the water until eventually they end up somewhere and they reprecipitate into a new crystal. And these non-clastic sedimentary rocks are the result of that. The chemical ones, anyway. There's another classification of non-clastic sedimentary rock called organic. Anyone know what this is?
Obsidian.
Not obsidian. Good guess. Got a chunk of it right here. This is an organic sedimentary rock called coal. You've heard of coal, right? Do you know what coal is?
What we get in our stockings.
What you get. This is what Jackson gets in his stocking.
Isn't it carbon?
It's it's a high concentration of carbon.
If you condense it hard enough, it turns into diamond, correct?
No, actually.
Then that's just myth?
That's just a myth, yeah. You can't actually turn coal into diamond. There was that thing that went around not that long ago where if you covered a piece of charcoal and peanut butter and you stuck it in the freezer, it would pull out a diamond, right? You guys remember that? It was the dumbest thing. Social media is so stupid. Social media puts our civilization further back than anything else, I think.
I think 5 Minute Crafts did that.
Yeah, it's ridiculous. I remember that year I had so many students asking me if that was real. And I had a few students that said that they tried it and they didn't do it right because it didn't work. I was like, no, that's not why it didn't work. Anyways, so yes, this is coal. Coal is high in carbon, but not exclusively carbon. Okay? Something that is exclusively carbon would be more like the mineral graphite. Okay? So, but you get coal by compressing plant matter super, super hard under heat and pressure. And that's how you get your coal. Now, how is this a rock? Because all that's left are essentially the components that you would find in minerals. Okay? It goes through the same process of making a rock, that heat and that pressure. You're just using decayed plant matter, okay, instead of bits and pieces of sediment. So coal is an organic, organic, non-clastic sedimentary rock, okay? That goes over here. Okay. You can also get organic sedimentary rocks made out of shells and skeletons, okay? I'll show you a few examples of that as well. All right, so let's talk about the clastic ones first. The most common physical weathered ingredients that are in clastic sedimentary rocks are quartz and clay. You ready for another logic train? Tell me why quartz and clay are the most common ingredients in clastic sedimentary rocks.
Because they're in the ground. I'd rather wait.
You're absolutely right that it has to do with weathering. Tell me why. Tell me how. Tell me where. Water, possibly. Water may be a process by which those materials are broken down. But of all the things we've talked about, all the different minerals we've learned in this class, why are quartz and clay the most common ones?
Because they're like in every rock.
Are they in every rock?
Not all of them, but like they're in a bunch of them underground.
Silica.
They yawn.
Yes. Do you yawn?
Yeah, I yawn. I just didn't know snakes did.
Yeah, they yawn. Was it cool or did it freak you out? No? It was fun, yeah. Like how wide his mouth gets when he yawns, it gets even wider when he's eating a rat. Yeah. Okay. You were onto something there. You were talking about how common they are. Is quartz pretty common on our planet? Tell me where and why.
Because it's a strong material.
It's strong, so it's harder to break down, sure.
It's like made of feldspar, isn't it?
Quartz? No, quartz is a completely different mineral than feldspar.
Isn't it everywhere?
Ah, quartz is extremely common. Why? Because those silicon tetrahedrons are the backbone of every silicate mineral. And so much of our planet, at least in the uppermost layers, are made out of silicate materials, right? So when you break down those silicate materials, often you get those silica ions as a byproduct. Where do you think we are more likely to find little bits and pieces of quartz? On land or out in the ocean? Ooh, why on land? What's the chemical difference between the igneous rock on land and the igneous rock in the ocean? Do you remember?
The pressure. Or something.
Not so much the pressure, no. Chemical difference is what I'm asking about. The chemical difference is what I'm asking about. Huh?
I said what it contains.
Yes, what they contain. But what is the difference? Like, what does one contain that the other does not? There's an inverse relationship we talked about early on. Louder. Okay, so the different compositions can form below and above ground. So it's not really that. It has everything to do with composition, but what? Do you remember what the general composition of ocean rock is, the ocean crust, versus the continental crust? Sand is a byproduct. It's a sediment. Do you remember the two composition words? One described ocean crust and one described continental crust? No. That's it. That's a component of both. The continental crust is mostly felsic, and the ocean crust is mostly mafic. Bingo! Mafic meaning high in iron and magnesium and low in silica. Felsic meaning high in silica and low in iron and magnesium. Which one of those two compositions is more likely to produce quartz? Felsic, which means we get more quartz production on continents or in the oceans? On continents. Are you tying this together in your heads yet? Are the dots connecting? Quartz is a very common ingredient in clastic sedimentary rocks because it is very commonly found in the felsic igneous rocks on continents. So then here's another question. Are we more or less likely to find a quartz, say sandstone, a clastic sedimentary rock, in the middle of the ocean or near a continent? Near a continent. And why?
Because it's made up of quartz, which are made up felsic rock that's found on the surface.
Bingo! Because that's where the quartz is. The quartz is a byproduct of the weathering of continental felsic igneous rocks. You won't find that in the middle of the ocean. Make sense? Great. Okay, so why clay? Why is clay another very common ingredient in clastic sedimentary rocks? Using the same logic cycle we just went through. I can give you a hint. Autumn actually started touching on this topic earlier when we were talking about quartz, but it was too early. What about feldspar?
On the surface, clay is made up of feldspar.
We got a heck of a lot of feldspar, that's true. Is it exclusively on land or in the ocean? It's present in both. Right. So we can, well, how does that tie to clay? Yeah, what process does it go through? Feldspar goes through what process at the surface? Huh? Yes, and we call that process weathering. Yes, and when feldspar weathers, it turns into clay. Yes, most clays are the result of weathering feldspars. I've got a buddy named Clay. He's about 10 years older than me. He's not a geologist, but I like to poke at him. When you were younger, your parents would have called you feldspar. He doesn't think it's funny, but he's not a geologist, so that's understandable. I chuckle, though. Yeah, I'm one of those weirdos that says a joke and then laughs at my own joke. No one else in the room might be laughing, but I do. I crack myself up. Okay, so that's why clay is another very common ingredient. Okay? Because feldspar is so common, therefore its weathering byproduct of clay must be present in a lot of places, and as a matter of fact, it is. Sedimentary rocks made in the ocean are high in clay. Sedimentary rocks on land are high in clay. Did you have a question? No? Okay. All right, any questions about that? That makes sense to everyone? Nod your heads if it does. If it doesn't, I'm going to assume I have to say it again. Faith, are you clear on that? Yeah? Okay, great. All right, now, while that's true, you can still have bits and pieces of unweathered, unbroken down materials in your sedimentary rocks. Something to keep in mind is that while we are identifying these sedimentary rocks, we are basing those identifications off of generalizations for the most part, okay? So when I say that this thing is a sandstone, it may have larger pieces in there. It's just that the majority of the pieces are sand, okay? So just bear that in mind. There may be see chunks like that in there, that larger piece of feldspar, and there's another one right there, and another one right there, and another one right there. But I would still call this a sandstone, even though there are a few larger pieces in there, okay? So how do we identify these clastic sedimentary rocks? Well, the first thing we're going to do that with is particle size. Grain size is another word for this. In your test kits, some of them, there are grain size charts, little plastic charts. I think I only have maybe a dozen of those things left. I used to have one in every test kit, but it's one of the things that unfortunately tends to walk off the most. It finds its way into pockets or backpacks. Please don't do that because I only have a few left. I need to go buy more at some point. But they, we'll have to share, is what I'm saying. We'll have to share the ones I've got until I can get more. Particle size or grain size is going to be the first factor here. Now there's a range, okay? Anything smaller than 1/256th of a millimeter, these are in millimeters, okay, is called a clay. Can you see that with the naked eye? No. No one can see that with the naked eye. Between 1/256th and 1/16th of a millimeter, we call that silt. Now, if you have perfect vision or better than perfect vision, then you can possibly see the larger ones of those, okay? I do not have perfect vision, nowhere near perfect vision. My wife likes to boast that she has 20/15 vision. I'm like, good for you. So she could probably see those. I cannot. I need a microscope for both silts and clays. 1/16th to 2 millimeters, that's called sand, okay? So when I call something a sandstone, what does that mean? That means that it is a sedimentary rock made predominantly out of grains that are between 1/16th and 2 millimeters in size. That's what a sandstone is, yeah.
What vision do you have?
What vision do I have? Brother, I couldn't even tell you. My glasses prescription is -6 and -6.5. That tells you anything. AKA it sucks. Yeah, it's pretty bad. If I wasn't wearing contacts or glasses, everything gets fuzzy this far from my face. I would not survive in nature without glasses or contact lenses. Huh?
You could say it's
You have -7?
No, he said if you got to -7.
What about if I got, if I got to -7?
Yeah.
I'd be dead. No, I'm kidding. Nothing else would, it would just be worse.
Because you keep saying 6, 7.
I don't understand the joke. All right. So that's sand. Anything larger than that, we call 2 to 4 millimeters a granule, 4 to 64 a pebble, 64 to 256 a cobble, and anything larger than 256 millimeters is called a boulder. That's a nice boulder. You guys get that quote? Do you get it? What's it from? That's a nice boulder. No?
Isn't that from the show where the boulder runs and like starts rolling at him?
No. It's Shrek. You guys, oh, come on. Yeah, the donkey says it. Yeah. Oh, come on now. We're not watching Shrek for our class movie night, but you guys need to watch that. Yeah, I know. I'll put out that questionnaire sometime soon. Okay, so particle size. Why is particle size so relevant? Why is it important? How can we use it to figure out information about the environment that this rock formed in, or that the sediment was deposited in, I should say? Any ideas how particle size, grain size might give us clues about the environment? Specifically the depositional environment.
Like what kind of pressure?
Not pressure. Let's see, Giovanni. Let's say that you went outside and you bent down and you picked up a rock about this big. That would take a certain amount of energy, right? Now let's say that I gave you a boulder the size of a car and I asked you to push it. Would that take more or less energy? So what can we figure out here? It takes more energy to move larger things, right? So the size of our grains that are deposited in an environment tell you what? What the energy was like in that environment. Do I have larger grains? Well, if I have larger grains, then how much energy did I have? A lot. If I have smaller grains, how much energy was present? Very little. Look at that. Now you know another way to figure out clues about the history of our planet. By looking at the grain size in a layer of sedimentary rock, you can figure out approximately how much energy was present there depositing those grains. Right? If I'm looking at very, very fine-grained clays, I might be looking at rock from the bottom of the ocean. If I'm looking at rock that's filled with chunks of debris this big mixed in with the rock, I might be looking at a very fast stream or a flood deposit or something. Right? Okay, next up, sorting. That is how similar in size these grains are to each other. Yeah. You may, yes. Okay, how similar in size the grains are to each other. Do I have 50% sand grains and 50% granule size? Okay, so you'll describe this by saying that it is well sorted, moderately sorted, or poorly sorted. The more sorted it is, the closer those grain sizes are to each other. So if I have tiny little sands and then big old cobbles, that's pretty poorly sorted. What can this tell us about the environment, the depositional environment?
Something in the move, the bigger ones than the smaller ones.
Hmm?
Like something, like there's like a change of like how they move.
There is quite a big change going on, but what is it? It does, in fact, come down to energy again. If I have large and small grains mixed up together, what's happening here?
It's uneven. It's not gonna be balanced. Well,
See that last part again?
I said it's not gonna be balanced, right? It's gonna be uneven.
I mean, it's not well sorted, right? So yeah, you're right. It's not balanced by size.
More or less energy.
Well, is there more or is there less? Let me ask you this. Oh man, it looks like my other microphone turned off. It must not have charged well last night. I'll get it in a bit. Yeah.
So if the rock scratches the glass, then it's harder than 5.5?
If the mineral scratches the glass?
Or yeah, if the mineral scratches the glass, it's harder than 5.5?
It is harder than 5.5, yes. Okay. No one has any ideas here? Let me ask you this. When I have a running river, it's going to have more energy based upon how steep the slope is. Do you understand that? The steeper my slope is, the faster my river is going to be running because it's going downhill faster, right? So is it going to have larger or smaller particles being deposited up there? Larger, right? As it ever so slowly makes its way further downhill and the slope decreases, the closer it gets to the bottom of whatever hill it's going down, its energy is going to drop. As its energy drops, it's going to be depositing larger, or smaller grains of sediment as we go along that progress. So up here at the top of the river, larger grains. Down towards the middle, the medium-sized grains, and then down at the bottom of the river, where it has the least amount of energy, it's going to be depositing those smaller grains, the smallest grains, right? So if I have a rock that is made out of a whole bunch of grain sizes all mixed and mashed up together, what does that tell you about the energy in my water? Did it decrease slowly over time or all at once? All at once. All of a sudden, all the energy in my water was lost like this, and every grain size was deposited at the same time. So this could be a landslide or an underwater slide of some kind. That's very common, okay? We get those off the coast all the time. It could be a flooding event. Anything that produces a large amount of energy, and then that energy immediately or almost immediately is removed from the system. And it dumps all the sediment it was carrying out at the same time. There's no opportunity for it to settle by size. Okay? So that's what looking at the sorting can tell you. Then there's the shape. Now, this is not the shape of the rock itself. It's the shape of the grains inside of it. Are they rounder or are they more angular? What would that tell you?
Would they have more surface area? Being weathered more?
Surface area, larger surface area gets weathered faster, and that produces what? The rounded corners, right? You remember this? Yeah, the rounded corners, you remember that? Yeah, good. Okay, so if my grains are more rounded, that means what for my depositional environment? Huh? What? Yes. You're just doing that to avoid the question, though, huh? Any ideas? Rounder grains means what? I want to hear what he said first, and then I'm going to come back to that.
There's no water for a long period of time.
Not that there was no water for a long period of time. Ah, there it is. Rounder grains means more weathering. Either it stayed in that same spot and just got weathered over and over and over, or it came a pretty long distance before it finally got deposited, right? Rounder grains means that sediment spent more time being weathered before it turned into that rock. Angular grains means that it didn't go through very much weathering before it got turned into that rock. Huh? Did you have a question? Yeah. No? Oh, I thought your hand was up. Are you scratching your head? Ah, gets me every time. Okay. Does this all make sense? Using these factors to identify clastic sedimentary rocks. You will have magnifying glasses. For those of you that are watching this, doing this class online, you have the videos. You can see in those HD videos as you're looking at them. And I have pictures next to grain size charts for you to identify grain sizes with each sample. Okay? Okay, let's talk about some of the more common sedimentary rocks. Let's start with shale. I can pass around both of these. All right. Shale is made from very fine particles, clay and silt-sized particles. Other words for shale, some people might call them mudstones. Some people might call them siltstones or claystones. Shale is a good general use term. However, mudstones and siltstones can also be found without any layers. Shale is typically layered, like this. So you'll see how it's kind of making these very thin, platey layers on top of each other, like that. I'll pass these around in a second. I'm just showing them to the camera right now. Okay, so made from very, very fine particles. What energy system was this sediment deposited in? Low energy or high? All right, who says high? Who says low? So many abstentions. Okay? It is a low energy system. And why? Because if it was a high energy system, you would have larger particles there. Right? The fine grains, those will never settle if there's any amount of energy there. So when you see something like a shale, you're safe to be assuming it's a very low energy system. Commonly, deep oceans. Shale is forming right now all over the planet wherever there's an ocean. When you get into deep water, there's almost zero energy in that water. It barely moves at all, which means that any sediment that gets washed out there by, say, a river makes its way out deep into the ocean and then ever so slowly settles to the bottom. Okay? The very, very thin layers inside of the shale, we call those laminations or laminae. Okay? That's what that word means. We also will often find fossils in shale. Also, shale is commonly the parent rock that is creating oil. Oil commonly forms in shales that contain a whole lot of organic components. Predominantly, the countless numbers of tiny little creatures and microorganisms and bacteria and algae that lived out in the ocean over the millions and millions and millions and millions of years. Okay? That's what makes your oil. How many of you learned that oil came from dinosaurs? Incorrect. There were, even for being on the planet for as long as they were, there were not enough dinosaurs to make oil. Bless you. Oil is formed from, bless you, from plants, algae, and bacteria, and microfossils, microanimals like planktons and zooplanktons that lived out in the oceans for way longer than dinosaurs ever existed. Okay? Then we've got sandstone. You want to guess what grain size sandstone is made out of? Sand size. Bingo. Okay? That 1/16 to 2 millimeters in size. All right? Now, sandstone's primary mineral ingredient is going to be quartz. This is an almost exclusively 100% quartz sandstone. Now, the quartz in this has the same properties as the quartz in your Lab 1. So when you scratch it on glass, it's going to scratch the glass just like the quartz in your Lab 1 did. Okay? Even though you had one distinct crystal there, and you have a rock made out of billions of them here, same properties. You just obviously you can't tell things like cleavage and crystal form and stuff like that with tiny little grains that have been weathered down. Okay? But it's still the same mineral. Sandstone is often the reservoir rock, the holding rock that oil is found inside of. In a conventional reservoir, it's usually some porous rock like sandstone with enough space between the grains to hold the oil. Bless you. There's so many sneezes on that side of the room. Should we like isolate you guys off? Call you the plague corner or something? I'm kidding, I won't do that. I left my caution tape at home. All right, sandstone. Now, there are varieties of sandstone, okay? When you have a sandstone that has a high amount of feldspar in it, 25% or more, we call that arkose. Okay, in this one, you could definitely tell. Look at that pink coloration. That's potassium feldspar. There's a lot of feldspar in there, okay? That is a type of sandstone called arkose. Still a sandstone, but we give it a different name to show, hey, there's something chemically different about this one than the other sandstones. When there's a high amount, that's 15% or more of clays or silts, we call that a greywacke, okay? That's this word right here, greywacke. So it's still mostly sand-sized particles. It may even still be mostly quartz, but there's a high enough amount of silts and clays in there that we give it a little bit of a distinction there by calling it greywacke. And the color is often thrown off as a result of that many clays and silts in there. Okay? Then we've got conglomerate. U and E. Let's do this one. Okay. With conglomerates, these are anything that have the majority of grains being larger than 2 millimeters. Okay, so larger than sand-sized. There are two different types of conglomerates. There's your true conglomerate, which we just call conglomerate, where all of the larger grains in there are rounded. Okay? So a conglomerate is often a poorly sorted mix of large grains and small grains. And in a normal conglomerate, all of those large grains are going to be rounded, well-rounded. And the other variety, which we call breccia, it's the same thing, large and small grains, but the larger pieces are angular. Okay? None of the larger pieces in this breccia have been rounded at all. Okay? So you've got your conglomerate and breccia, which are both conglomerates, but we call breccia something different because of the angularity of the fragments. What energy do you suppose we get that in? Don't look.
Wait, what was the question?
What energy do we find conglomerates forming in? Yes. High? Do we all agree high? Yes, it's in high energy. Why? Because of the large particle sizes. Great. You're catching on. Any questions about clastic sedimentary rocks before we move on to inorganic chemical sedimentary rocks? Huh?
Some of the rocks that are on the ground, because it's like some of them are igneous rock. You know what I mean? Like they can find them in the fluid.
So conglomerates are often crushed up for use in gravels and concretes and stuff like that. That's why it kind of looks like concrete. Concrete is essentially artificial conglomerate. Okay? Concrete, cement, all of those things. We're essentially making rock ourselves.
This one is made out of skull, right?
Made out of what?
This is made out of skull. Like out of skull.
A skull? No.
Oh no.
No. That one is chert chunks that are being held together by calcite. Okay. Yep. All right, no questions about clastic sedimentary rocks? No? All right, chemical sedimentary rocks. Remember, these are the ones that are made from those microscopic chemical ingredients. As previous rocks are dissolved, their components are flushed away into the groundwater system and then recombine at some point. Okay? The first way that they can recombine is through evaporation. What happens if I dissolve a bunch of sugar or salt into a glass of water and then let that water sit out for a while? Louder. The water evaporates away and leaves behind what? What's it going to leave behind, Emily? If I have a bunch of salt water and the water evaporates away, what stays? The salt. Bingo! I get all the salt left behind. As that water, more and more of that water evaporates away, what's left becomes more and more enriched in the remaining salt. Because that salt can't go anywhere. And so you're going to start seeing salt crystals form at the bottom of your cup. Until finally all the water is gone and you're just left with salt crystals. Okay? That's one way that this can happen. If I have water that is rich in dissolved minerals like calcite, as that water evaporates away, it's going to leave behind deposits of calcite. Okay? Travertine is one example of this. This is a spring in Yellowstone National Park where the groundwater, so it's underground, is flowing through layers of limestone. As it flows through the layers of limestone, it dissolves the limestone and becomes enriched in calcite. Once that water reaches the surface and starts running over the surface, it's starting to evaporate away, and so it leaves tiny little layers of calcite that build on top of themselves, making these cool step-like travertine deposits here. This happens all the time with salt and gypsum in places where bodies of water used to be. If you ever drive through Utah, have any of you ever driven through Utah? If you do, wear sunglasses. It gets blinding. Because there are wide stretches, especially in central Utah, where it's just deposits of salt and gypsum left behind from when there used to be a much larger lake there. It evaporated away and left behind all of the dissolved minerals that used to be in there. Okay? Then you've got your organic sedimentary rocks, the ones that are made from shells, skeletons, plant matter, stuff like that. Okay, so it'll look something like this. All of these are fossils, and the fossils have gotten mashed together and made this rock. We call this limestone. Let's talk about the different varieties of limestone. Limestones are very common. They account for about 10% of the total amount of sedimentary rock on the surface, which is actually pretty astonishing for one classification of sedimentary rock to make up that much of it. Okay? Yeah, sure. Okay, so different types of limestone. Let's start off with, I'm actually going to go to the bottom first and talk about inorganic limestone first. Okay, this one right here. Limestone is made out of calcite. Calcite, CaCO3, is made, is precipitated through a couple of different varieties. The first one is temperature change. If I asked you, let's see, Anik, if I asked you to dissolve something in water, what would you usually do to that water first? Well, let's assume that we haven't put the thing in the water yet. What's your first step with that water if I want you to dissolve something in it?
Put it in a bowl.
Sure, it needs to be in something. Huh? Heat it up, right? If you wanted to dissolve salt or sugar or really anything in water, you would typically heat it up first, right? For most things, that would work. Fun fact about calcite. When you actually heat up the water that contains the calcite, It precipitates. Okay? When you cool off the water, it dissolves easier. Weird. This has a couple of implications. First of all, in paleontology, that's really cool because I can look at what my shells, my fossil shells, are made out of in a limestone or in any rock, really. And if I see that they are mostly made out of non-calcite things, something like silica, I'm probably looking at a cold water environment because no animal is going to make their shell out of something that can dissolve, right? That's not very good survival. And so they adapt to make their shells out of stuff that won't dissolve. And so I'm looking at a cold water environment if it's made out of anything but calcite. If I'm looking at a exclusively calcite-made shell system, then I'm probably looking at something a lot warmer, possibly even tropical. Okay, so that's the first thing. The second thing is, when you get a whole lot of calcite that is precipitating in the water, you get deposits of microcalcite crystals at the bottom of the ocean. They precipitate out in the water, slowly fall down through the water column, and then land on the ocean and make layer upon layer upon layer upon layer of microscopic calcite deposits. And that makes this type of limestone called micrite. This is micrite limestone, made from microcalcite crystals. Okay? This is made out of calcite. You can drop acid on that, and guess what? It's going to fizz. Just like the single crystal of calcite I gave you in the lab. Okay? Then we've got, there it is. We've got fossiliferous limestone. Also made from calcite, but the shells of animals that used the calcite in the water to grow their shells, and then they died and they fell to the bottom, and all of their shells got compressed together, and that made this fossiliferous limestone. Same properties as what I just passed around, just made from shells instead of microcrystals. This will fizz when you put acid on it as well. Okay? There are massive deposits of this stuff, not actually that far away from us. Do any of you recognize this picture by any chance? You know where that is? That's the Guadalupe Mountains. That's not that far from us. That's just further west a little bit. A couple hours drive. Huh? New Mexico, yeah. The entire Guadalupe mountain range is one massive reef. From when all of this used to be covered in water, okay, this entire region of the country used to be covered in water, and that was one massive reef system that grew underwater. And now it's all fossil limestone. So you can go climbing, you can go hiking or caving. I go caving in the Guadalupes. You can go over there, and there are fossils literally everywhere because it's just one big reef. Okay? Fossiliferous limestone. There are a couple of other different types of limestone we can get. Let's see. This is called oolitic limestone.
Wait, what was this?
That's fossiliferous limestone because it's made out of fossils. Fossiliferous. Yes, fossiliferous. Okay. Oolitic limestone is made out of tiny little nodules of lime, of calcite, that form in shallow, warm water, like the Bahamas, Jamaica, right? I think these ones actually came from the Bahamas. Yes, Bahamas, okay? So what happens is you get those little microcrystals that form, they go to the bottom. But because we're talking about shallow water here, there's some back and forth motion. And so our crystals are doing this at the bottom of the sea, slowly moving back and forth. And as they do that, they pick up more and more calcite on their outer surfaces. They grow larger, but they also get rounder as they're moving back and forth until you get deposits of oolites, which look like sand, but when you do the tests on them, you'll find they're made out of calcite, right? And when those get compressed together, you get oolitic limestone, which looks like sandstone until you do the tests on them. Another reason why it's important to know your mineral tests, okay? That's a bag of oolites, and that is a piece of oolitic limestone. I wouldn't open the bag because if you spill any on your laptop or something and it gets in the keys, you'll never get them out. Yeah, they're tiny. Yes, of course. And then the other two varieties of limestone, we've got coquina, which looks like this. Think of this as kind of pre-limestone. It's a bunch of shells that have not been fossilized yet, but have been fused together. Give it a couple 100,000 more years of compression, and this becomes fossiliferous limestone. But right now, it's pieces of shells that have gotten fused together. Okay? And then this is chalk. You guys have used chalk before, right? You know what chalk is. You've heard of chalk, right? I don't have a chalkboard, but classrooms used to. Chalk is made from the fossilized skeletons of microscopic animals. These are plankton bodies and dinoflagellates and coccolithophores and radiolarians and a whole bunch of foraminiferans, a whole bunch of tiny little animals that lived in the ocean a long time ago, fell to the bottom of the ocean, their bodies got compressed together and fossilized and made chalk. It's essentially a form of fossiliferous limestone. Okay, that's what chalk is. This picture I have on the PowerPoint, right here. These white cliffs right here, these are in England. These are entirely made out of chalk. Huh? It looks like food? Oh boy, careful. If rocks start looking good enough to eat, you might be a closet geologist. Yeah, just a closet geologist. A geologist, someone who would be a good geologist but doesn't want to admit it to themselves or to other people. Okay, so these entire white cliffs here in England, this is all chalk. Can you imagine how the sheer number of microscopic animals had to live in the ocean to build up a layer of chalk that thick? Look at this white dust on my hand from holding that chalk. Every little particle of dust on my hand is a microskeleton of something that was alive in the ocean. Huh? Yeah, they look like, maybe some of them look like little bugs, but yeah, you get some ocean water and you look through a microscope, you'll see some planktons in there, buddy, right now. But during the time period that this was all deposited, there was so many more than billions, my man. There are billions in that little rock I'm passing around right now.
The one with the chalk.
Yeah, the chalk. That chalk is made out of billions of skeletons. Imagine in that cliff. And that cliff goes for miles. That layer goes miles and miles and miles and miles and miles.
That thing was like dust on my hand.
Okay, moving on. Dolostone. In the same way that calcite and dolomite are very similar to each other, you learned about these on the lab. Hopefully you've come across both of these on the lab already, lab 1. In the same way that calcite and dolomite are very similar, the only difference being that dolomite has an extra magnesium ion attached to it. Limestone and dolostone are similar in the same way. Dolostone is essentially limestone with some extra magnesiums in the equation. This interferes with identification a little bit because they look almost exactly the same. It's just that dolostone does not fizz immediately. You have to powder it first, just like you did on the lab. Okay? We're not exactly certain how this happens. Dolostone very well could be limestone, but some water passes through it and attaches magnesiums to it, something like that. We're not entirely sure about this process yet. It's still being understood. The problem is it would take so long to test the theories about how to make it that not all of the tests are practical to do. So people are still working on that, though. They're so similar, though, dolostone has to be a byproduct of some change to limestone. Chert. Yes, of course. Chert, also known as flint or jasper. These are microcrystalline quartz rocks. So you remember how I told you these agates form? I mentioned this last time. These agates are formed when those loose silica ions from the weathering of silicate minerals passes through the water system, the groundwater usually, and then starts building up inside of empty spaces in the rock. And you eventually get these solid, or mostly solid but partly hollow, buildups of silica bands, silica layers inside. And that's what makes agates. That's also what makes geodes. A geode is simply an agate that didn't finish getting built, that didn't finish filling in. Okay? That's how you form chert. That's how you form flint and jasper. All of these mean the same thing. Okay? And then you've got your evaporites, like salt and gypsum, like what we talked about earlier. Okay? Those are also inorganic, non-clastic sedimentary rocks. Then we've got coal. Now, I already mentioned coal, but I'm going to take you through the whole process of how you form coal now. You are a plant. Congratulations, you're a tree. You live a good life in the forest. You grow tall. You put out a lot of seeds. You're surrounded by your sapling offspring. And then something happens. Maybe you get struck by lightning. Maybe a beaver chops you down. Maybe a dude with a chainsaw cuts you off. Whatever the case may be, eventually you die and you fall to the ground. Wham! You're on the ground. What happens next? You're already dead by that point, right? But you start to break down. Unless you happen to be in the right sort of situation. If you are in a swamp or a marsh where there is lots of standing water that does not get refreshed very often, what will usually happen is that water will become anoxic. Have you guys heard that term before? Anoxic? What does anoxic mean, do you suppose?
I was like repeating the words.
Anoxic. Juliet, any ideas? Anoxic? What it means? If saying something has oxygen, if I said oxic, that would mean something has plenty of oxygens. What would anoxic mean, do you suppose then? If oxic means it has oxygens, anoxic must mean it doesn't have. Right. An anoxic environment is one that has lost or does not have any free oxygens. Okay? Here's a fun fact. Did you know that oxygen is what's breaking down your bodies right now? Did you know that you are currently aging because of oxygen? Your cells are breaking down under the influence of oxidization. Your DNA, your DNA is commanding your body to replicate cells, to make replacement cells, but it can't keep up with it. And so as time goes on, our bodies just can't keep up quite as fast as they used to, replacing these cells. But we keep on getting our cells destroyed by the oxygen that we need to survive. This is aging. It's an interesting process. There are lots of people who are very interested in trying to figure out how to stop the oxidization of our DNA and our cells. Yeah?
And you just like breathe slower.
Breathe slower and age slower? Is that how that works?
You just hold your breath.
I think you would just pass out, brother. That's not how it works. But there are lots of people interested in figuring that out, because if you could, theoretically, figure out how to stop ourselves from degrading under the influence of oxygen, we could be talking about much longer lifetimes. Probably not immortality, but much longer lifetimes. Okay? Interesting thought there. But this tree is going to degrade, it's going to rot away unless it's in an anoxic environment, like what you would find in the water of a swamp. So now let's say you're a tree and you go splash and you fall into this swamp water. It's anoxic now. You're not going to rot away. Instead, what happens is another tree falls on top of you, and then some other things fall on top of you, and then maybe you're covered in sediment, and then another tree. And as time goes on and more plant material is buried in this swamp, it's going to get pressurized and heated the deeper it goes underground. The more pressure it goes under, your organic plant material turns into something we call peat. This is peat, compressed plant matter. Camera's not following me. Right here. There we go. This is peat. You can still see the little stringy planty bits coming off of this, right? It looks kind of like mulch that I compressed together. That's essentially all it is. I can burn this, and I can get heat off of it, and I can make energy with it. It would also stink like heck, right? It would not smell good. But you could. That's the first step in making coal. Now, if I were to take that, and where is the, there it is, and compress it even more, heat it a little bit more, that process of heating and pressurization is going to remove some of the other things in there. It's going to resemble less plant material. It's going to look more like a rock, although you can still see some leaf impressions and stuff in here. It would take about 3 feet of plant material to make 1 foot of peat. It would take about 3 feet of peat to make 1 foot of lignite, which is what we call this. Super compressed peat right here. Okay? Real compressed. This burns a lot cleaner than that peat does. Still isn't as efficient as what we're getting to next, but it's a lot better. Okay? There's a lot of energy tied up in this. All you have to do is light it on fire, and a lot more energy is released. That's the secret to fossil fuels. It takes energy to release the energy, but you get a lot more energy out of it after you light it up. Bless you. Okay? So this is lignite. The next step after lignite is bituminous coal, which is the coal that most people think about when I say coal. When anyone says coal, this is what you're typically thinking about. This is what Jackson gets in his stocking every year, right? This is what most coal power plants do burn. This and lignite are what fueled the Industrial Revolution. This is what built the society we have now. This is what got us to the point where we could use things like crude oil. Okay? A substantial amount, and I want to say it's somewhere just below 40% of power still comes from coal.
Is that what they use for trains? Like, that they did use for trains?
Right. A lot of trains were, and some still are, coal-powered. Why is it rainbowish? Yeah, there's a little bit of iridescence in there, huh? That's the organic compounds in there, okay? It's just the way that they're arranged inside of the structure. It's reflecting the light back that way. Now, there is actually, yes?
So what's the difference between those two coals?
Between the lignite and the bituminous coal?
The one that you showed us earlier, like yeah, I guess what's the difference between those two coals?
The two that I'm passing around right now. Anik is about to hand off lignite. What you're holding right now is peat. That's the first step. That's compressed plant matter. When you cook peat a little bit more, you get lignite, like what Chris has. When you cook lignite a little bit more, you get bituminous coal, like what Faith has. Okay? Now, there is another step beyond that. When you take bituminous coal and you bury it even further, you heat it up and pressurize it a little bit more, we have now entered into a brand new system called metamorphism, which you will get the full picture of on Tuesday, next week. But this gives you anthracite. When you metamorphose bituminous coal, you get anthracite, which looks like that. Kind of takes that iridescence to a whole new level, doesn't it? Yeah, it's super shiny. This is as close as we can get to pure solid fossil fuel energy. This burns extraordinarily cleanly. Almost no emissions as a result of burning this. It's a beautiful power source. None of these are technically renewable. Well, I mean, technically, I suppose they are. It just they renew over millions of years, which doesn't do us any good, right? So why don't we use this for everything, you ask? Why don't we have anthracite burning cars? Why don't we have anthracite burning houses? Why do we bother with the other fossil fuels if anthracite is just that pure and that great? Very limited. This is formed at very deep depths underground. The heat and pressure it takes to make this out of bituminous coal is very deep, which means that we don't have a lot of this at the surface, which means that we cannot use it commercially, at least not very much. You can go and buy anthracite pellets for your houses, right? And there's enough of it that you can just go to the store and buy some. Probably not Walmart. Tractor Supply probably has some though, right? But there's not enough of this that we can power every power plant in the country with it. Okay? It would be nice if we could put out a whole lot less emissions. But that's not the case. Okay, there's that word, diagenesis. Diagenesis is any change that occurs to my sediment after deposition, but before metamorphism. Okay, so what does that mean? I'm heating and pressurizing my sediment. There is a threshold at which I'm going to do that and enter metamorphism. But for now, we're going to talk about everything that happens before that. Okay? So between 150 and 200 degrees Celsius, it's okay, just pick it up.
Nice job so far.
Just pick up all the pieces if you don't mind. And then keep passing them around. So between 150 degrees and 200 degrees Celsius, and a few kilometers of depth, you are in the pressure and heat threshold for diagenesis to occur. So the most common thing that we see happen in diagenesis is the process of turning sediment into sedimentary rock. That is called lithification. You want to say it with me? Lithification. Yeah, good. There you go. No, you can't keep it. I need to keep all those pieces, please. Okay. Lithification. When you take your loose sediment and compress it to the point where it becomes a rock. Okay, so there are a few aspects of this. There's your compaction. There's actually a surprising amount of air and even water between all the grains in a loose sediment. So when you compress it, most of that gets squeezed out. All the spaces get filled in with the sediment that's there. Okay, so you're compressing it and then cementing it. Any dissolved minerals that are in that water that you're squeezing out are going to precipitate between those grains, often as a result of the increasing heat. Okay, so this can include cements can include things like calcite, silica, iron oxides, just whatever is there in the water in your sediment. Okay, so you're compressing and then cementing. And then by the time the pressure is released, you've got a rock. A clastic sedimentary rock. Okay? So, what do we know now? We know that we've got classic sedimentary rocks. We know that we've got chemical sedimentary rocks. We know we've got organic sedimentary rocks, right? We know that there are different textural differences, okay? Some non-classic textures that you can see, by the way, crystalline, like the micrite, microcrystals that are that form together. Skeletal, like that fossiliferous limestone I passed around. Oolitic, like that oolitic limestone I passed around. Organic, like the coal that I passed around. Okay, so we've been seeing all of these common examples of sedimentary rocks today. So what can we do with this information? Knowing what we know now about interpreting igneous rocks and interpreting sedimentary rocks, we can paint a pretty fun, accurate picture of the history of the Earth in a given location. right? You don't even have the whole picture yet, though. With metamorphic rocks, you can do a whole lot more. You're learning how to answer questions. Yeah? I do not have a broom. The janitors should come in and clean that up later, though. Okay? You're learning how to paint a picture of the history of our planet. Okay? How to figure it out, how to answer these questions. So this is an image that's just supposed to show you some places on a generic map of where you would find locations where sediment is being deposited in different environments, right? At a beach, for example, what grain size would we typically find at a beach?
Little sand.
Sand, which are technically medium-sized grains because silts and clays exist, right? But you would get sands there, right? And what kind of rock would commonly form from sand? Sandstone, right? Okay, well, what about at a swamp? What kind of deposits do we usually see in a swamp? Is there a lot of flowing that's carrying sediment, or is there a lot of organic plant life living and dying? Yeah, organic plant life, and you were going to get a buildup of coal there, okay? So these are different places around where you can see where these rocks would form, okay? Where these sediments would be deposited and where those rocks would form. Okay. Now, inside of these sedimentary rocks, we see sedimentary structures. A structure is just another clue, but it's a clue as to the processes that were happening at the same time that sediment was deposited, or sometimes shortly before or after that. Okay? Bedding planes. In this formation, and in most rock formations you'll see these kind of cracks between the different layers. Those are showing you bedding planes. Bedding is simply another word for a layer of sediment, okay? A bed of sediment. And so the bedding is the differentiation between those different layers. Why is that there? Why does the bedding exist? Because something changed. Maybe this layer had sand-sized particles. Maybe this layer had larger particles. Maybe this one has lots of cement. Maybe that one has very little cement. Maybe this one's poorly sorted and this one is well sorted. Something changed, and that's why the two layers are distinct from each other. That is bedding. Okay? Then there's cross bedding, which looks like this, where you have a layer that's deposited at that angle, and then another one that's deposited at this angle, and then another one that's at that angle, and at that angle, and then at this angle, and then at that angle. Ooh, here's an interesting question. Can you think... No? That's just your answer?
She asked for this thing and I said no.
Oh, okay. I was like, here's an interesting question. No. Ah, all right. We've reached that point already. All right. Under what circumstances would we see layers of sediment deposited at different angles on top of each other like this? Water doing what? Angelina, right? Okay, what do you think? Under what circumstances would we see sediment being deposited on top of itself or on other layers at different angles? Should I simplify it? Should I take it back a minute? Under what circumstance would we see sediment deposited at an angle to begin with? Instead of being flat, why would it be at an angle? Huh? Okay, so water is doing something. It doesn't have to be water, but it's doing something to that sediment. What's it doing? Assuming that, I mean, sure, weathering is continually ongoing, but it's already sediment, so it's been weathered to the point where this water is having some effect on it. Or wind, by the way. Just want to throw that out there. Huh? It's pushing it. And what's it pushing it into? A pile. What do we call a pile of sediment that's been pushed by the wind or water?
Loose sediment?
It's already loose, that's why it can be pushed. Huh? Well, sand in this particular case, this is sandstone, but any sediment at all. It's making a deposit, but in a certain form. We live not that far from a place where wind is constantly pushing sediment up into piles. What do we call that? Huh? A dune. Right? When wind or water pushes sediment up into a sort of pile, we call that a dune, right? We have a whole lecture coming up about deserts. We'll talk about dunes specifically there. Okay, now we know under what circumstance wind or water will push sediment up at an angle onto the side of a pile of sediment that we call a dune, as an example, right? Now, why would we have sediment deposited at this angle here, and then at this angle here, and then at this angle on top of it, and then at this angle on top of that? Not two different sources. The wind or water changes direction. So here, in this cross bedding, we see sediment deposited at that angle. And then the wind or water changed direction, and now it was deposited at that angle. And then at this one, and then at that one, and then at this one, and then at that one. That's called cross bedding. And cross bedding is a dead giveaway that the direction of deposition has changed. And I can actually figure out what those angles are and then put together a timeline of what the predominant wind or tide directions were that deposited that sediment. More clues, more facts, more data points. Then we've got things like ripple marks like this. From flowing water or wind, it will make ripples in the sediment like that, like little dunes. And then mud cracks will be preserved in the rock as well. All sorts of structures can be preserved in rock and give insight into the environment at that time. Then, of course, there are fossils. Fossils are preserved in sedimentary rock. These are also structures that give us insight as to what the environment was like at the time. These are all fossils that I have found. Some of them are here on this table. These are all fossilized tree pieces. Got one right here. I found these in Montana. Actually, everything on the slide I found in Montana. This is, yeah, this is a tree that's been replaced by silica. It is a rock, my friend. Fossils are rocks.
I mean, I wouldn't have thought it started as a tree.
Yes, well, that's the point of a fossil, right? It starts off as something that was alive, and then cell by cell, been replaced by a mineral of some kind. This tree, in this case, replaced by silica.
So this is a tree.
That's a fossil tree, yeah, replaced by quartz.
And so the light inside of it, like the light color,
The colors are depending on what was in the mineral that replaced it.
that was silicon, right?
In this case, silica, yeah, that's essentially turned into microcrystalline quartz. But it's maintained a lot of the shape and grain structure of the tree.
This part looks more like a tree.
Yeah, exactly. Yeah. This is a Tyrannosaurus rex rib that I found while I was out there, but obviously it was too encased in the rock to remove, so I just photographed it. This is a turtle shell right there that I found. And then these are the pieces of the eyebrow structure of a Triceratops skull.
How do you know that?
When you stare at enough bones long enough, you learn to be able to recognize them. I've spent lots and lots and lots and lots and lots of hours with dinosaur bones. So once you put the pieces together, it's pretty easy to tell. Okay, so here's the problem. Here's the story with this, though. After taking this picture, I was excited. I was like, man, these are pieces of a Triceratops eyebrow. This is fantastic. So I took the picture, I put my camera down, and I started moving the pieces around, trying to see how many more things I could find, because that's how you do it. You document the location, and then you can move the things around to try and figure out how many more pieces you've got. You always want to document things in their original location, though. Underneath of those, I found the rest of the Triceratops skull. Uncovered about a square foot of it, right? Found the eye socket, found the frill. As far as I could tell, the whole rest of the skull was there under the ground. But that was the last day that I had a permit to dig at this location, and I had no time to take out an entire Triceratops skull. So I covered it, marked it with a flag, and then told the local university where it was so they could send a team to remove it because I didn't have enough time. But I forgot to photograph the rest of the skull. I was so entranced with what I had found, and I had already taken a picture. It completely slipped my mind to take more pictures of the rest of what I'd found. So it wasn't until I was on my way home and I was going through my camera, I was like, no. But I got the eyebrow structure. The rest of the skull I hoped it went back for. Yeah? No. No. So here's an important fact, right? Vertebrate paleontological remains, that means anything that had a backbone, so dinosaurs included, okay? It is illegal to remove those from public land or private land, okay? Unless you are the private landowner. If it's your land, you can own it. You can do whatever you want with it. But they are federally protected items, okay? That means that if I had, this was on BLM land, Bureau of Land Management, so publicly owned land in Montana. If I had attempted to remove those, I would have gone to jail. I had a permit, so I could remove them, but they had to go to a local university or museum. I had the permit as part of a local museum dig, and so it would have gone to the museum. But if I had tried keeping them for myself, that's grounds for imprisonment.
Can you purchase them? Like, if you dig one up, can you buy one?
No, is what I'm going to say the legal answer is.
So if you would have kept them, what would happen? You would go to jail, but what would the charge be?
The charge would be theft of federal property.
How long would you be in jail for?
I don't know what the exact time is. I feel like it's probably 1 to 5 years. Depends on the severity of the theft and the property in question. Since I had a permit, a federal permit, I would be in direct violation of that permit by keeping it for myself. So it probably would have been worse than if I had just been out there on my own digging, because I could have claimed I had no idea that that was a law or something like that. Having a permit and then stealing the thing, that's worse.
Yeah.
Because I'm well aware that I needed a permit to dig in the first place, right? Actually, this will happen every now and then. Someone will buy or steal fossils and then face the consequences. Nicolas Cage has one of the largest private fossil collections in the world. Part of the reason why he's in so many movies is he's always on the verge of bankruptcy. Yeah?
What happens if, say, you dig it up and the property owner says
Yeah, you could. If you dig it up on private land and you have written authorization from the landowner that it can be yours, then you can keep it because it's his property to do with. That varies by state. In some states, landowners have limited mineral resource rights to their property.
So this still, of course, can happen, of course, right? People can go out and some places like that, like forest or river, like look for those.
Oh yeah, it happens all the time. Oh yeah, totally. And you can keep as many pieces of fossilized tree as you want, right? I mean, depending on the location. But yeah, generally no one cares. Little shells, like the little clam shells and stuff like that, no one really cares if you keep those unless they're from specific locations. But anything that comes from a vertebrate.
So you got that from there, and they let you take that home?
Oh yeah. Yeah, fossilized trees. We have fossilized trees in spades wherever you go, really. Tons of them.
They have fossilized trees.
Yeah, there are places not that far away. New Mexico and Arizona have a lot of fossilized trees. Yeah. There are places only within an hour's drive from here that I could take you to go and look for fossils. I would actually love to do a field trip with you guys. I would, except that most of y'all are high school students. And do you have any idea how much paperwork I would have to go through to take you guys off campus? It's worth it? It's worth it to you. I'd have to do all the paperwork.
What would you have to do?
I'd have to get permission from the college. I'd have to get permission from your high schools. You'd have to get permission to miss your other classes that day. And then I would have to rent a bus. And for anything larger than 15 passengers, you need a bus driver that has a CDL. There is so much I'd have to go through to try and make this happen, guys.
My friend's dad did drive for us.
Your friend's dad? Not someone certified by either the high school or the college, and so that wouldn't work.
But they have a CDL.
but not certified by the college or high school.
Hey, sir, wait.
Oh, we do a lottery system, and then, okay, so I'll take 3 people. You can go in my Jeep. We'll go on a weekend. It won't be an official school trip. Let's go.
Yeah, would you actually allow that, sir?
No, I can't do that.
Could you have those, like, the field trip? Could you try it?
Could I try and do a field trip?
Try and do a field trip?
Pff, not for this semester, dude. Like, we have 6 weeks left in the semester. I bet you that I would not get a yes or no answer until the end of the 6 weeks. Yeah, that's how long this process would take. It's a system that I would love to get going, but it's right now not practical. By the way, I also have this chunk right here. I didn't find this one, but this is also fossilized wood.
Oh, wow.
Yeah.
That's crazy. It looks like it's made out of a table.
Yeah, people make tables out of this stuff all the time.
So, and that's when you are a geologist. Like, whenever you know, like, what minerals and all that.
You know you're a geologist when you can tell what the minerals are? Well, that should mean that you're all geologists by the end of the class, right? Okay, so yes, fossils. All right, yeah.
How long did you study to be a geologist?
Technically, I still am. So I started college in 2010. I got my associate's degree in 2011. I started my bachelor's degree in 2015, graduated in 2017. Started my master's degree in 2018, graduated in 2020. Started my PhD in 2022, and I'm supposed to graduate in 2028. So I will have been in school for a total of 15 years. Of the last 18 years, by the time I get my PhD, of the last 18 years of my life, I will have been in school for almost 15 of them.
So you've been in school like pretty much your whole life?
Not my whole life, brother. How old do you think I am?
38?
38? It's, yeah,
Or 40?
40? 60? I don't understand what that joke is, brother. All right, I'm 31.
Oh, 30. Oh, you're young.
Oh, thank you. It's the beard. The beard throws everyone off. Everyone always thinks I'm way older than I am, right? You should have seen me. I had a beard out to here a few years ago. So when I started teaching here at the college, I was 25. And I had a beard out to here, and so everyone always thought I was in my 40s.
Getting like 50.
But I was like, I'm 25. And at that point, I didn't have that many high school students yet. I still had a bunch of older students. And half of my class would be like, I'm so depressed that my college professor is younger than I am. But that doesn't happen that much anymore. Yeah, I'm 31. I'll be 32 in November. Okay. Let's talk about the non-metallic resources, okay? Because a lot of those do come from sedimentary rocks, okay? Apatite. You guys remember apatite. Who's found apatite on Lab 1 already? Yeah? Okay. By the way, I hope y'all are done with Lab 1. You really should be starting work on Lab 2 because you're getting Lab 3 today, okay? Highly recommend that you get that turned in, okay? Apatite is a mineral that we get phosphorus from. Very important, very important. Phosphorus is essential for life. We use it a lot in fertilizers. We use it in match heads, stuff like that. But also, fun fact, your teeth are made out of the mineral apatite. Yeah, your body harnesses all of the ingredients that it needs to grow a mineral, and it grows that mineral into the shape of your teeth for chewing purposes. How crazy are our bodies, right? It's literally an incredible biological machine, okay? Asbestos, calcite, diamond, fluorite, graphite, muscovite, quartz, sulfur, all of these things are things that we use in our daily lives, okay? We require these things, and they all come from, well, for the most part, they come from sedimentary sources. Here's a list of all of the things that the typical American utilizes within 1 year, okay? 5,713 kilograms of stone, 137 kilograms of clay, 35 kilograms of aluminum, 3,500 kilograms of petroleum. All of the things that you see here, everything you all use each in 1 year. But you're like, wait, I don't remember using 6 kilograms of manganese, right? Well, these include the things that our community utilizes. So things like for power plants, for production of your breakfast cereal, stuff like that. And the cost of it, the resource cost of it, is spread among every American. Okay? So every American, on average, requires this many resources to function, to survive in our country. Look at how many resources we all use. Do you know where all these resources come from?
Our Earth.
The Earth. And you know who finds them?
Geologists.
Geologists finds every single one of those. Yeah, good job, Jackson. The point being, geology is essential for more than just curious science. Civilization would die tomorrow if all the geologists stopped working. Right? Well, it would start to die tomorrow. It might take a few years for it to fully kick the bucket. But things would start going downhill immediately. Okay? Look at all this. 37% of all of our power comes from petroleum, 23% of it from coal, 24% from natural gas, 9% nuclear power, 7% renewable energy. You remember when President Biden was in office and he started that initiative to have the United States be fossil fuel independent, or to be completely off of fossil fuels by 2050? Every car needed to be electric and all of that. That was never going to happen. Never. How do we go from 7% to 100% in 20-something years? You don't. You don't. Let me give you some thoughts here. Has there ever been a form of fuel that humanity has ever used that we no longer do? What was the first form of fuel that humanity used? No. Wood. Burning fuel, making fire with wood. Do we still do that? You bet we do. What was the next one? Coal. Do we still use that? You bet we do. What was the next one? Yes. What was the next one after coal? Huh?
Gasoline.
Oil. And natural gas. Do we still use that? You bet we do. We have never, ever left behind a form of fuel. We will never stop using fossil fuels, my friends, no matter what politicians say. That's not how the math works. Okay? We will keep using it. Even if nuclear and wind and solar are things that really take off, if we can take that 7% and make it 70%, we will still be using fossil fuels. Less of them, sure, and great. Less emissions. We can get a handle on that, but we will never fully leave it behind. That's not realistic. Yeah?
So was that little chart next to the big chart everything that goes into renewable energy?
Yeah. So of that 7%, 53% of it is biomass, 7% of it is wind, 5% is geothermal, 34% is hydroelectric, and 1% is solar. 1% of that 7% is solar. For us to make enough solar panels to power the United States, let's say just the houses of the United States, not even all the businesses or transportation needs. For wind power, you would have to cover an area the size of New Hampshire and Delaware together, completely in wind turbines. Which doesn't sound like much because those are two of the smaller states, but that's an incredible amount of resources. Do you know how much of our planet we would have to strip mine resources from to make that many wind turbines?
Probably a lot.
Enough to offset the whole point in the first place. You'd have to cover an area the size of the Sahara Desert to power our country with solar panels. Not ever going to happen. Not without strip mining our planet to oblivion. So it's real easy for a politician to say, I'm going to get us off of fossil fuels by yada, yada, yada to get elected. It's an empty promise. Anyone that actually understands science and math knows that can't ever happen. And now you do too. So don't fall for those empty promises. Okay? By the way, I'm not just picking on Biden or Democrats or anything like that. Republicans make empty promises too. There's no perfect answer to our system. There's no perfect politician. They all say what they need to say to get reelected. Okay? Empty promises all around. But now you know how to think critically and do the math. Okay? This is the distribution of coal resources around our country. Everywhere you see that is red, that's bituminous coal. Okay, so we've got a lot of that. Everywhere you see that's this kind of orangish, this subbituminous, and this brown is lignite. Okay, so there's a lot of it up here. Okay, and this goes even further north into Alberta. Okay, there's a lot of it up there. Everywhere you see that is black has that anthracite. How many places do you see that have anthracite? Yeah, there's just these 3 locations along the East Coast. Again, that's why there's not enough of it for us to use commercially. Okay? At least not widespread commercialism. Okay? Really quick, I want to mention to you, and this will be the last slide, I'm going to mention to you how hydrocarbons form, okay? Specifically oil and gas. A long time ago, in this particular example, it says 300 to 400 million years ago. That's as good an example as any, although it doesn't have to take that long for this process, okay? The oceans filled with microorganisms, those planktons, those zooplanktons, foraminiferans, especially foraminiferans at this point in time, okay? Radiolarians, dinoflagellates, coccolithophores, fantastic, wide varieties of really fun names to say of microorganisms living in the water, okay? Every time they die, they fall to the bottom. 1 billion things fall into the bottom a second. However many that is a year. For hundreds of millions of years. Falling to the bottom of the ocean and then getting covered in sediment and incorporated into the sediment and turned into rock, and all of those organic remains get cooked. They get heated, they get pressurized, and they slowly turn into a liquid. That liquid is what we call crude oil. That crude oil seeps through the rock until it finds a zone of lower pressure. Usually it's some sort of geologic high. What that means is, if there's some deformation in our rock that makes a sort of, excuse me, a higher point like this, maybe some tectonic force pushed a section of rock up. Well, if that's the case and you get that sort of high inside of the rock, all the oil in the area is going to flow up there because that high represents a point of lower pressure inside of the rock body. So you get a pocket of oil there. It's going to stay underground because it can't go to the surface. As it gets cooked longer, it starts to change its state. The longer that oil gets cooked, the more it turns into natural gas. Okay? So if we get to a body of a pool of oil soon enough, we'll poke our straws down there and yeah, we'll pull up oil. If we poke our straws down there and all we get is natural gas, well, that tells us that we found the right location just a couple million years too late. It got cooked too much. Okay? That's what natural gas is. It's crude oil that got overcooked. Okay? Any questions about that? So why do we have a lot of oil here then? Are we anywhere near the water? Are we anywhere near the ocean? Huh? This used to be ocean during a time period called the Permian. That's why this place is called the Permian Basin, my friends, because during the time period called the Permian, guess what? This was all underwater. That's when those layers of sediment filled with those microorganisms were being deposited. Since then, this whole area has been covered in sediment, and all those layers of organics-rich rock, those organics have turned into oil and natural gas, and now we poke our straws down through all the layers of rock that have been deposited on top of it, and we pull those up. That's why this is the Permian Basin. That's why the Permian Basin is filled with oil, because the Permian time period, this was all covered in water. Cool? Any questions at all from today? Okay. Lab 3 is now assigned. You have your sedimentary rocks lab assigned. I've already talked to you about all the properties for sedimentary rocks that you need in the lecture today. There is a Lab 3 PowerPoint that gives you a refresher on all of those things and gives you some extra resources. There are 12 samples for this, just like there were 12 samples for Lab 2, so it shouldn't take you as long as Lab 1 did by any means. If you have not completed Lab 1, get it done ASAP, because you should be well through Lab 2 or turning in Lab 2 ideally, because you really don't want to fall behind. Okay? Use your time well. Use your best judgment. You do not want to fall behind, because before you know it, we're going to be at the midterm, and you might still be really behind on labs. Okay? Alrighty, I'm going to end the recording here.